in the context of Berry phases or the Berry problem, they really give you the same outcome, or they describe the same geometry, they give you the same equations as Berry's original discussion of Berry phases. And so it is justifiable, it is to call this modular Berry phases. This is really the same conditions as Berry had, only generalized, extended appropriately. Okay, so what do these things mean? Let's imagine that I have diagonalized the Hamiltonian, so I can write it in this form. And again, this is not the dynamical Hamiltonian, this is the modular Hamiltonian. Now, there are two, and then we're asking the question, in what way can this modular Hamiltonian change as we are going from one region to another region? So roughly speaking, there are two distinct types of changes to H mod: eigenvector changes and eigenvalue changes. So eigenvector changes can be generated by a commutator of the modular Hamiltonian with some new operator V. And a good basis for possible V's will be these off-diagonal antisymmetric matrices, such as En Em minus Em En. So when you write it down in the diagonal basis for H, such V's look like 1 minus 1 someplace and zeros everywhere else. Basically, these look like rotations where we are rotating one of the eigenvectors into another eigenvector. Okay. And V is the generator of such a rotation. Now, there is a second type of change to H, which is, what if we just change the eigenvalues? So I keep the same basis for H, but I am changing around the eigenvalues. Because H has to be, e to the negative H is the density matrix, and the density matrix has satisfies the condition that trace of rho equals 1. We can't really independently vary these energy eigenvalues. They have to satisfy an overall condition such that the trace of e to the negative H has to be equal to 1. But within that scope, we have some freedom of readjusting these eigenvalues. And so this is another type of change we can have. Now, these types of changes, the eigenvalue changes, cannot be generated by a commutator of anything with, of H mod with any operator V. So, and also notice that these types of changes are precisely the zero modes of H. Namely, if I take such a delta H and I ask, does it commute with H? The answer is yes, it does. They are diagonalized in exactly the same basis. And so we understand that from this we see that these two different types of changes to H can be classified by whether or not the change itself is a zero mode of H, or if it is not a zero mode of H. When we go back to our condition number 1, I see that I am trying to generate a change in H by a commutator of something, but then I'm allowing myself to miss the change by some zero modes. What are those zero modes? These would be precisely the changes of the second type, the eigenvalue type. So I will want to find a V so that it matches and exactly it produces the right change of the first type, the eigenvector change, but I understand that I will never be able to match an eigenvalue change for a commutator, so I'm taking it out from dH mod in this equation. Okay, so that's why, and this is what I'm saying here, because the eigenvalue changes in H are zero modes of H, because they cannot be generated by a commutator with anything, therefore we take them out in equation 1. That's what we just saw. And such variations, the variations that affect only the eigenvalues and not the eigenvectors, simply don't count towards our parallel transport. We ignore them in checking what parallel transport is. Okay, so the explanation for the first equation is this one. When I write down this equation, what I'm really saying is find a V which generates that part in the change of H mod that can be generated by a commutator. And the part that cannot be generated, okay, forget about it. Okay, so that's equation 1. Then I have equation 2, or condition 2 really, which is that V should contain no zero modes of H mod. So how do I understand that? Let's say that I have some V which satisfies this condition number 1. I'm already done with condition 1. And now I'm asking, well, what happens if I add to my V some V0, which is a zero mode of H mod, then obviously V plus V0 is still a solution of this equation. Because I just added a homogeneous equation that doesn't, and a homogeneous piece which doesn't affect it doesn't produce anything on the right-hand side. And so that means that when I'm solving for V, I'm always getting answers which are ambiguous up to zero modes. And the whole point of modular parallel transport is to find the golden V, which contains exactly no zero modes at all. So how do I do this? Well, there are various ways in which we can implement this, but here's one simple way of implementing this, which is this. Remember that zero modes cannot be obtained by V commutator H mod. So that means that if I manage to obtain a V with a commutator of something else, an H mod, that V will precisely have no zero modes in it. So I can look for precisely that V, which can be written in the form some yet another operator commutator of H mod. Why does this work? Because I know that such commutators can never produce zero modes, and I'm looking for a V which is zero mode free. These guys will always be zero mode free. And so this is one practical way in which I can implement condition 2. But condition 2, we can study it also.
Sorry to interrupt. So this is like, I mean, it's a sufficient condition, but I mean, is it also necessary? Like, I mean, the fact that you can write in this way.
It's necessary and sufficient. Correct. It's necessary and sufficient because we can think about the commutator of V with H mod. No, a commutator of anything with H mod as a linear map that takes operators to operators. And so what we're really doing is we're trying to say, I want V to be in the image of this map. But if I mod out the, how to say this, there are various V's, but there is, what I'm trying to do is mod out by the kernel of this map, I guess is the right phrase. I'm not using the right phrases right now. But the point is that if you think about this as a linear equation that just sends us a linear map that sends operators to operators, by eliminating these zero modes, we're precisely eliminating all ambiguities, and we're down to a unique solution at that point. And so this is the right map to do it. I'm sorry for not being clear on it. I'm blanking out on the right usage of words like kernel and image, but it really works this way. Okay. And so hopefully this is an explanation for what the two conditions are, okay? So the two conditions are find the guy which is as good a match as possible for the variation in H mod, as good as possible given that we're trying to use commutators. So zero modes will not be matched by commutators, but everything else will be other than zero modes. And then find the guy which itself contains no zero modes. That's what we're looking for. And now the question that we want to talk about is, how do I find such a thing, or on the bulk side? So what would that mean? But so far the discussion was completely general. I didn't assume any holography. I just stated a geometric problem which could be studied without any thinking about holography. In fact, it can be studied in quantum mechanics. It's just a completely general quantum mechanical and geometric problem to solve. But now we're trying to turn on some holography and see if there is a bulk description for these things. Okay, so let's remember to study what this means in the bulk. Let's remember about what H mod really is from the bulk point of view. And what it is that it's a symmetry of the entanglement wedge in the neighborhood of the RT surface, remember? And in that, well, it's always a symmetry of the entanglement wedge, but it acts geometrically in the neighborhood of the RT surface. And in the neighborhood of the RT surface, it acts like a boost. Okay. So with these facts, we look back at this, we look at these two equations, and we're asking the following question. How do I take the generator of a boost in the neighborhood of one RT surface, commute it with something else, and I get another, I get the change in the boost, so that the change plus the old guy gives me a new boost about some new RT surface. That's really what equation 1 is giving me. So how to phrase this more explicitly? the idea is we represent H mod as a vector field psi near the RT surface. This vector field will generate boosts about the RT surface. So this is what we have drawn so far here. And then the parallel transport is supposed to map this psi, so this one of these vector fields, to another vector field subject to an extra, which is the boost by the new RT surface, with some extra conditions. So we have, again, this is a picture that says what I just said in equation. This is a picture that just represents what I said. I have one initial boost. I will have some new boost after the RT surface has been affected. And I'm hoping that I can find some yet another object, which will also be a vector field, such that when I commute it with the old vector field, I'm just getting the difference between the vector fields, the new one minus the old one. In equations, I'm looking for some eta, which will also be a vector field, such that the commutator with the first boost generator gives me the difference of these boost generators, plus possibly some zero modes of psi, namely, plus possibly some vector fields that actually commute with psi. And that's how we will construe the first equation in the bulk in the language of vector fields. Now you might ask, when is it valid to switch from the language of operators in the CFT to the language of vector fields? And here I am using it as an assumption, and I'm hoping it's true, that the magical thing that makes it work is the code subspace projection. Before the code subspace projection, these operators are just completely general operators in the CFT, but we know that one of these operators, H mod, is represented near the RT surface actually by a vector field which generates boosts. So we know this fact from, well, prior papers, and here the primary reference I would give is Aitor Lewkowicz and Tom Faulkner's paper, but also JLMS going before that. So there is an established literature which tells us that if I get close enough to the RT surface, we talked about this yesterday, that this general H mod, which is some a priori arbitrary operator in the CFT, in the code subspace acts like a vector field. I am now imagining that there will also be that the solution to the modular parallel transport problem, the V we were describing a moment ago, can also be represented as a vector field. And I'll tell you that if that's the case, I'll tell you what properties that vector field does. And this guy ought to be the code subspace projector of the V we found in the CFT language. Okay, and so yes, this is an equivalence that we will be assuming. There's also the second condition, which is that eta, the generator of modular parallel transport in the code subspace, the vector field that represents it there, contains no zero modes of psi. And that just means that's supposed to be equivalent to the statement that V contains no zero modes of H mod. So what are the zero modes? And yes, well, they are vector fields that commute with psi, but what are they exactly? Like the next thing we have to talk about is how to visualize the zero modes of psi, since the zero modes were so important to our definition of modular parallel transport. Then we will talk about how to eliminate them from eta and what this tells us about eta. Right. So let's talk about these zero modes. Parallel transport is supposed to contain no zero modes. So here what I did is I created a table where I talk about various vector fields that we can have in the neighborhood of the RT surface. And I arrange them into two rows. One is vector fields that point along the RT surface, and one is vector fields that are perpendicular to the RT surface. So these are just, a general vector field will be a linear combination of these two. And I want to ask, are they zero modes or are they not zero modes? And remember that if we find that something is a zero mode, that means that it has to be excluded from our parallel transport. So what's in this table? The first thing to say is that whatever components we have along the RT surface, by definition, because they're pointing along the RT surface, they preserve the RT surface. And if they preserve the RT surface, then they are by definition zero modes. So that means that parallel transport will necessarily have no components along the RT surface. And then we have the directions which are orthogonal to the RT surface. This is an RT surface is a codimension 2 surface, and we have two null directions which are orthogonal to it. So what are the approximate isometries of this, or what are the isometries of a very small neighborhood of a point on the RT surface in the two transverse directions? We have a boost, and we have the two translations in the time and space directions. And so the statement here is that boosts are precisely those symmetries which preserve the RT surface again. Now we're moving in directions orthogonal to the RT surface, so we're really just talking about a single point on the RT surface, and on that two-dimensional plane which is orthogonal to the RT surface at that point, a boost is exactly that symmetry which doesn't do anything to the RT surface. It preserves that point. So boosts are, of course, generated by C1 itself. They are generated by H mod. And these are the zero modes that we'll want to exclude. On the other hand, there are also two more things we can do in a 1+1 dimensional orthogonal plane. Namely, we can do translations. And translations, these translations are going to be fibered over the RT surface, because nothing tells me that I have to translate by the same amount this point and that point and that point. So in general, what I'm left with after excluding both the diffeos along the RT surface and the boost are all types of translations in the two orthogonal directions. But these translations, again, are fibered over the RT surface, namely different points will get translated by different amounts. Okay, and here I drew just sort of two extreme cases of what can happen. So in one case, I will be translating my point maybe in the same way here and there. This looks like a rigid translation that's acting on the RT surface. And an opposite situation, qualitatively speaking, is if different points on the RT surface will get translated in opposite directions. What do we call this? We call it a rotation. When I have a rigid object and I translate one piece of it one way and another piece in exactly the opposite way, that's what a rotation is doing. And so rigid translations and rigid rotations are the sort of extreme cases of what modular parallel transport can do to a surface. But of course, there are more intermediate cases where different amounts of translations act at different points in a less concerted fashion, and then it's more complicated to. There isn't a word to describe this kind of thing. Okay, so here this picture is just saying that translations can happen at every point of the RT surface, but independently at every point. Okay, so a summary of what parallel transport in the bulk can do is that it has no components along the RT surface. That's what we concluded here in this line of the table. It has no boost component in the two orthogonal directions, but it can have translation components in the orthogonal directions. And the translation components, if they act in a concerted fashion, then this is like a global translation. And they act in an anti-concerted fashion, this is like a rotation. And lots of options in between also apply. Okay. Are there any questions about what modular parallel transport can do to a surface? So what I will talk about next is examples of how this thing is actually realized in the bulk. But maybe I should just give a bird's eye view of what we have done. We have written down a set of equations to describe a geometric notion of parallel transport. This notion of parallel transport was directly inspired by the Berry connection, but now applied to modular Hamiltonians. It gave us a bunch of equations for something that is just well defined in any quantum mechanical system, and in particular in a CFT, which is holographic. And what we just did just a moment ago is to ask, is there a bulk representation of these equations? And based on symmetry considerations, this is it. This is what we just found. So it's an interesting way to encapsulate something that is very intuitive in the bulk using definite equations that are meaningful from the boundary point of view. That's really the motivation and the philosophy of this work. So I now want to give examples of what kinds of things can be modular parallel transport can produce for you, both in terms of its curvature and in terms of the holonomies. These are the two things that are interesting about modular parallel transport. So the first thing that we can look at is, suppose that I'm in a 2+1 dimension. I don't have to be in the vacuum. It doesn't have to be pure ADS, but some asymptotic ADS2 geometry. And I'm moving from I'm using modular parallel transport to move from one interval to another interval. It's best to draw this, if I'm not using any time in this picture, to just focus on an equal time slice, which I have drawn here. And so I'm going from this interval here to the larger to the other interval to the right of it over there. And then I'm asking, what does modular parallel transport do? As in, what is a vector field that modular parallel transport produces in the bulk? And the answer is something called rotation without slipping. So let's understand this a little more. So when I map this interval to this interval, then what I really have to do is to map this endpoint to this endpoint, and I have to map this endpoint to this endpoint. Now, let's say, and that it turns out to be true, that I'm just going to use global conformal symmetries to do this. As we all know, global conformal symmetry on a circle, a rigid diffeomorphism on a circle, have three generators. That's L0, L1, and L-1. But I just gave you two conditions. The left endpoint has to be moved here, and the right endpoint has to be moved there. So there is a third unspecified condition yet, and modular parallel transport is supposed to specify it for me. The statement is that that third condition produces something called rotation without slipping from the bulk point of view. Namely, I'm going to use a conformal symmetry, which is the unique symmetry, which is actually a rotation about this point where the two geodesics intersect. And if you think about this for a moment, this is the only thing that does not break. This is the only option for going from this interval to the other interval that doesn't break conformal symmetry in some way. Any other way of moving from here to here would be an arbitrary thing which is non-covariant, in the sense that you have put in some non-covariant choice for how you're going to do it. This rotation without slipping is really the only way of moving from the interval to the other interval which does not break conformal invariance in any way. Well, how else would you not break conformal invariance? If you're going to map this geodesic to this geodesic, you have to specify where a point on one geodesic will end up on another geodesic. Well, and then let's think about it. Where does the point where they intersect, where should it go? If I take a point on this geodesic and then I map it to some point on the other geodesic, it could end up here or there or there or there. But if it maps anywhere else, my map would introduce a scale, which is the distance from where the point was to where the point ends up on the new geodesic. The only choice that doesn't break conformal symmetry and doesn't introduce a scale is to set that distance to 0, which means that if there is any point common to these geodesics, it just has to be fixed. I hope that this explained why that is a very special type of motion, and it's a unique motion that doesn't break conformal invariance in any way. And I hope that I have explained why it is called rotation without slipping. I find these two geodesics, and then I rotate from one to the other. What I could do is, in addition to the rotation, do a little bit of a translation along the new geodesic. That would also be a conformal symmetry. That new extra translation that I could have added would be what I call slipping. And so we're doing a unique type of rotation without slipping. Eliminating the slipping is exactly what we did in our condition 2. The slipping would have been a 0 mode with respect to our modular Hamiltonian, and eliminating the slipping is what condition 2 really does for us. Okay. So here's a picture of what kind of holonomy we can get. Imagine that I start from some geodesic and then I move to another and to another and to another geodesic. And just to keep track of what the holonomy does, I'm going to first focus my attention on some particular marked point on this geodesic, and I marked it with an X. So what I'm doing is rotating about the common point to these two geodesics, and I'm rotating from here to there. Then I will go from this interval to the next interval. That means that I will be rotating about a new point, which is this one, common to these two geodesics. So now my X point, the point where it got moved, will get rotated from about this point, from here to some new location along the new geodesic, that's here. And then I will do the same thing next, which is I'm going to the next geodesic in line, I find the new intersection point, and I rotate this guy over again about a new point. And I keep doing it, and I keep doing it. And I hope that you can see, well, first of all, I hope that you can understand what geometrically happens to the point. But second of all, I hope you can see that with every time that we are rotating, we are receding further away from the common curve that lives on the border of these geodesics. Is that clear or not? Because every time I'm rotating, I'm rotating away from the curve, sort of more into the interior and away from the curve. So every time I'm getting farther and farther away from the curve inside. Okay. When I come back to the initial geodesic, so that means after I have made a closed loop in the base, I come back to the same modular Hamiltonian that I started. This point will have gone much, much further away from where it was, and it will maybe end up here. The difference between where it started and where it ends is the holonomy of this vector field. And now the question is, what is that holonomy? Well, if you think about it for a moment, the amount by which the point is getting further and further away from the curve is really the sum of the distances from the neighboring rotation points. That's this amount and this amount and this amount and that amount. This is the amount that gets added between one step and the next step of the rotation. So here I was rotating about this point from here to here, but now I'm rotating about this point. So my radius of rotation got increased by the distance between the two consecutive rotation points. So the holonomy is going to be the sum of all of those distances between pairs of consecutive rotation points. And what is that? In a smooth limit, when I don't have a discrete set of geodesics, but a continuous one, this is going to be just the length of this curve. And so the holonomy is a translation along the RT surface, but it's not any old translation. It's a translation by the amount, which is exactly the circumference of the curve inside these geodesics. This is what's called differential geometry, and there is a formula for it. And that formula is, is this. So I just wrote it down for you. But even without writing down the formula, well, maybe I should say this. In the formula, S is the length of a given geodesic. And what we're doing here is taking some particular integral transform of all of these entanglement entropies, so all of these geodesic lengths that we have encountered along the way. But even without knowing this formula, just purely geometrically, you can see that the holonomy is going to be precisely equal to the circumference of the curve. And so I declare this a big success for the program already, because we discovered that when you draw a curve in the bulk of ADS and you ask what is the circumference of that curve, you're really computing some kind of Berry phase, except that the Berry phase is now valued in translations along an RT surface. And the Berry phase is the holonomy of a Berry field of a modular Berry connection, So this is our first application of what modular Berry phases are in ADS. Lengths of curves are just that. Okay. Notice that the holonomy is valued in the set of zero modes. That's always true. Remember our picture? Oh, and here I forgot about it. I have a picture here for what this looks like in the language of our bundle. See, we started at some point where we have a little geodesic, and then as we go along, we're making a closed loop, and the little region that I marked here is getting rotated. See? The region gets rotated until it comes back to where we started. And then the X's here are those special points that I have marked along the geodesic, because fibers, remember, choose modular frames. And here in this context, modular frame is just a choice of modular frame is simply a choice of a special point on the geodesic. And now remember, in general, modular frames are the sets of coordinate systems. maybe I will explain the point about how frames are just points along the geodesics in the next slide. I just realized that I haven't said this yet. But in this context, a fact is that different modular frames are just different choices of points on the geodesic that I could have chosen. And you can see this because fibers are zero modes. And in this case, the relevant zero modes are just translations along the geodesic. So I can think of the fiber as just being the set of points along this geodesic. So I started with some particular point here, and then I have some rule, which is rotation without slipping, that takes me from here to here to here. After I have closed my loop in the base space, I landed in a place which is different by some amount in the fiber directions. That amount turns out to be just the length of the curve that these geodesics traced in the bulk. Okay. So this is our example one. Are there any questions or comments about that? If there are no,
I have one question. So does this, like, I mean, where is the ADS coming here? Like, I mean, apart from the fact that you have a boundary, etc. Like, I mean, does it actually depend on being ADS precisely, or I mean, it seems to me more general than just ADS.
Yeah, there is nothing that special about ADS at the level of specifying a vector field that satisfies these conditions. And then we had yeah, so we could have written down such, we could have gone out in a search for vector fields that satisfy these conditions without any holographic motivation. But then we wouldn't know that these are Berry phases in any way. It would just be sort of an arbitrary geometric description of some new parallel transport. So it's because I know that there is a holographic dual that I know that these vector fields I'm looking for are actually code subspace representations of some operators that act on some Hilbert space in the boundary. And those operators have a direct Berry phase interpretation. Yeah. Okay, so this was one example of what a Berry phase can do. Let's talk about the curvature of this guy, because that curvature is really interesting. So remember what curvature was supposed to be. I was supposed to go from one point in the base to another point and another point in 2 steps, and then go there to the same place along the same steps in opposite order. And I was supposed to take the difference between them. This is the commutator of the θ1, θ2 directions in kinematic space, in the space of regions. So, and whatever the mismatch is there, the little holonomy for this infinitesimally sized closed loop is what we call the curvature. So let's talk about the curvature for this Berry connection. Now, I'm supposed to be taking for the curvature steps in 2 different directions in the base space. One, because our base space consists of intervals, a very natural set of coordinates for them is 1, the coordinate of the left endpoint, and 1 is the coordinate of the right endpoint of the interval. So these are good coordinates. So let's just take theta left and theta right, the location of the left and the right endpoint, as the coordinates and go through this exercise. And so I drew a picture here. This is not the cleanest picture ever, but here is an interval, and I can move the right endpoint in some way. I can move the left endpoint in some way. And imagine what happens if I first move the right endpoint, and then maybe I'll start from this one. First move the left endpoint and then move the right endpoint, or first move the right endpoint and then move the left endpoint. So in the end, I will have produced 4 geodesics. Here is maybe the smallest geodesic. Then I can move the left endpoint and I draw this one. Then I move the right endpoint and I get the biggest one. Or I could have first moved the right endpoint and I would get this geodesic, and then move the left endpoint and again draw the big geodesic. Yes. Overall, I definitely mark 4 geodesics, and these 4 geodesics correspond to the 4 points over here. And then we ask, what is the curvature? What is the curvature of this of the holonomy that I have traced in this way? Now, these geodesics don't mark in general when I have a holonomy for geodesics that draw a a convex curve in the bulk, then I know that the holonomy is just the circumference of that convex curve in the bulk. That's what we just talked about over here. But these guys are in a different regime. They don't actually draw a convex curve in the bulk of ADS for me. So I can't just import the answer from the previous slide. So you have to calculate it. But the way to calculate it is you can just take the formula for the holonomy that we had over here and just blindly plug into what it is without the regard for the interpretation as the length of a curve. We just use this formula, which was proven for us in some paper that I happen to have written 7 years ago, and go ahead and apply it to this particular little closed loop. And when you get this, you find that the curvature is this object here. You can actually read it off from here because the curvature has to be an exterior derivative of the integrand of this formula. And the exterior derivative takes this form. So this is maybe the easiest way to see that it had to be that. I'm not going through in detail through the algebra of this calculation because the algebra is not the illuminating part about this. Let's just take, if you can't follow the algebra, let's just take my word for it that this is the outcome. And then let's think about what this means. So imagine that I'm taking the second, as for the curvature, I'm getting the second partial derivative of S, which is the entanglement entropy of the region with endpoints at theta left and theta right. A second derivative as I vary the left and the right. And then I get a wedge product of the d theta left and d theta right. Let's think about what this quantity means. Imagine that I should have written this on the slide, but imagine that I call this region B. Oh, I have it here. Imagine that I call this the middle region B, and then the small little regions that are adjusted to it, which are d theta left and d theta right side, I'm going to call them A and C. So imagine that I can use discrete language for all the three regions together. That means if you discretize this second derivative, that means that the curvature is equal to the S, which is the entanglement entropy, for the region AB, that's the length of this geodesic, plus S of BC, that's the length of this geodesic, minus S of ABC, which is the length of this geodesic, and minus S of B, the length of just the smallest and small interior geodesic. This should have been a B here. If you look at this formula, there is something really special about it. This is called, this is a combination which is known as, it has a name, it's called conditional mutual information of A, B given C, A and C given B. But more importantly, this quantity is known to be always positive, and it is always positive because of the strong subadditivity of entanglement entropy. And so the curvature of our Berry connection is a quantity which is known to us from studies of formal quantum information theory. In the 1970s, an inequality was proven, which is the strong subadditivity of entanglement entropy. And that inequality is exactly of the form, this quantity is greater than or equal to 0. So we know that our curvature has a definite sign, and the curvature is a quantity that has definite quantum information theoretic significance. If you remember our slides from the beginning, I told you that for abelian fields, and this is an abelian Berry connection, the holonomy can be computed as an integral of the curvature. Remember we had this picture with the magnetic field where the holonomy was equal to the area that the magnetic field would take up. This thing is an exactly identical or an exactly analogous situation where I can compute this holonomy, that is the length of a curve, as an integral of this curvature. And so what we're learning here as a bonus is a statement that the length of any curve in the bulk of ADS can be computed as an integral of this curvature 2 form, and the curvature 2 form is nothing but strong subadditivity of entanglement entropy. It's a quantity which is always positive and which has some information theoretic meaning. So this gives us a quantum information theoretic interpretation of lengths of curves. And we wouldn't have known about this if Mr. Berry didn't come along and give us this language about curvatures and Berry connections. So here is our first application of modular Berry connection. Yes, Yanis.
So just a question. So coming back, to this point of view that, in principle, you can do this without holography, right? So shouldn't there be some kind of intrinsic, definition of this quantity, on the geometry side?
Yeah. So there is actually a field of geometry called integral geometry that I wrote a paper about it, popularizing it for physicists doing holography, where you can study spaces not as a collection of points, but as a collection of geodesics. And if you use that language of geodesics and not points, and that's kind of what we're doing here. We're treating the modular Hamiltonian, which is whose stabilizer set is a geodesic, as a basic thing that we are manipulating. So geometrically, we're really just moving RT surfaces, which are geodesics. And in that language, you can try to describe the bulk geometry. There are some limitations on it, but in many cases, you can literally describe everything there is to know about the geometry just by moving, never talking about points, only talking about geodesics. And this is the language that you would be using for that.
Yeah. So somehow then this is intrinsically connected to Riemannian curvature?
It's are you referring to what I promised in the beginning of the talk?
Also, yes, but now you said that alternatively I can treat, I can, instead of describing the space in terms of points, right? In that language I would have Riemannian curvature. Now you can describe in terms of this.
That's really the next thing I want to talk about. So let me just talk about the next thing.
Okay, sure.
So here I have a summary of example 1. The holonomy is the length of a curve. The curvature was this object, which was really strong subadditivity from quantum information theory. Now let's do example 2. And example 2 is not really much of an example. It's just a more general discussion of what can happen. And that, I think, will answer Yanis's question. So let's say that we're talking about some more general trajectory in asymptotically ADS 2+1 still. And let's recall some of the sort of general but abstract features of the problem we're studying, which is we have this bundle and vertical directions consist of 0 modes. And let's remember what those 0 modes are, because we had them in a table some time ago. They're either RT preserving diffeos, so things that move alongside the RT surface, or they are boosts. Boosts are really the only thing that can act orthogonally to the RT surface and also preserve it. Yeah? And so these things, both the alongside and the orthogonal boost freedom is what the 0 modes are. Whereas the fiber directions will be, we can travel in the base directions by everything else. Okay. So a question you can ask is, what is the object that actually transforms under the modular Berry connection? What I mean by this is that for the Berry phase, I could have given an abstract characterization of the Berry parallel transport problem. But if I always talked about the projectivized Hilbert space and never talked about the complex Hilbert space that we usually talk about with phases, then I wouldn't really know what physical thing actually transforms under it. I have to talk about states that have phases in order to know what actually carries that holonomy. In this case, what is the object that carries the holonomy that actually transforms when we change 0 modes? And so the statement I want to make is that this object is a coordinate system in the neighborhood of the RT surface. And specifying a coordinate system takes 2 things. I have to make a set of ticks on the RT surface, because the idea is I'm asking, what is it that changes when I change 0 modes, when I move from one point to another point on the fiber, when I change modular frames. So if I have a set of ticks and I use this freedom, obviously the ticks will get reshuffled and one tick will go to another tick. So that's definitely part of how I specify a coordinate system in the neighborhood of the RT surface. And another thing is a set of orthogonal, is like an orthogonal frame. because if I use a boost, then this frame can be mapped to one frame, can be mapped to another frame or to another frame, and that's what boosts do. And so, but this information, this set of ticks plus a little frame, is exactly what I need to make a small choice, a choice of coordinates in a small neighborhood of the RT surface. And so different gauges or different modular frames in the geometric language are basically different choices of coordinate systems in the neighborhood of an RT surface. And so that's the answer to the question, what transforms? What transforms is a coordinate system near an RT surface. And so now that we're armed with this knowledge and we understand that we should be tracking little coordinate systems in the neighborhood of an RT surface to understand what the holonomy does, let's see what the holonomy really could do. But actually, I have one more point, which is a preliminary to this, which is let's try to do this kind of exercise, not for a whole RT surface, but for just a single point. And then we'll get back to RT surface. So here is, imagine that I have an RT surface that doesn't have any longitudinal direction. It's a RT surface in 1+1 bulk dimension. So the surface is just a point, yes? You could do this in ADS too, actually. And then all we have now is for our coordinate system near the RT surface is just this frame, okay? And now what I'm supposed to do is move the point, so move my RT surface in one direction and another, and then another and another to form a closed loop. And this will tell me about the curvature. So what can happen then? Maybe this frame got transformed into this frame, and maybe this way the frame got transported to this frame. And then when I form a closed loop, I'm seeing a mismatch, yes? Going this way gave me this frame, going through the bottom trajectory gave me this frame. The mismatch between them is what we call a holonomy, in this case of a zero-dimensional RT surface. And then let me ask you the question, it's a rhetorical question, have we seen this picture before? And the answer is, this is exactly how the Riemann tensor is being introduced in textbooks on differential geometry. I imagine that there is a point, which is a framed point and carries some frame, and I take this point around a infinitesimal closed loop, and I ask, how does the frame transport? And the first two indices of the Riemann tensor correspond to the first directions in which I am moving my point, and the other two things on the Riemann tensor basically tell me how the frame itself gets rotated. So these x and y indices here just tell me about the rotation from one to the other. So if I work in 1+1 bulk dimensions, if I'm in ADS2 and I try to use this formalism, then I would be literally talking about the Riemann tensor when I talk about the curvature of the Berry connection. In higher dimensions, it is not literally the same, because in higher dimensions, I'm transporting the whole surfaces, whereas the Riemann tensor is still about transporting things point by point. And so this is the statement that I had before. It's that the curvature of the Berry connection is almost like Riemann curvature, except that it is carried surface by surface instead of point by point. So really, we should think of the Riemann curvature as some kind, maybe Berry curvature, as some kind of an integral transform of Riemann curvature. And the integral transform just basically integrates the Riemann curvature with some along the area of the RT surface. So I have this equation, it's not an equation, but a schematic equation. Modular Berry curvature is like Riemann curvature, but integrated along the area of the RT surface. And of course, they have some extra indices. So there will be some intrinsic vectors that soak up the indices from one side to produce the other side. But that's the relation between them schematically. And so I think that since we are used to changing bases in physics and going, for example, from the position space to momentum space, integral transforms are nothing formidable. So I think that on a moral level, we're allowed to say that modular Berry curvature is a set which includes Riemann curvatures in the bulk as its subset. Okay, it's not only that, because as we have seen, strong subadditivity of entanglement entropy is also part of modular Berry curvatures, but it also includes that. It only doesn't include it in ready-made form, point by point. It's in this, it contains it in this integral transformed form. Any questions about that?
I have one.
Did
Yes. So
I answer your?
yes, you did answer it. Yes, thank you. But now I have a related question. So the positivity constraint, right? I mean that you get generically from this berry phase, right? I mean the positivity of the mutual information shouldn't reflect into some kind of positivity then for the Riemann tensor, at least like I mean in 2 dimensions.
No, because the and so the answer is no, or not that I know of, because it doesn't give me any direct positivity of the Riemann curvature. But I'm thinking about whether some statement can be extracted in this fashion, and it might be. So yeah. So because of these extra longitudinal directions. Okay, so here we completely ignored the directions in talking about this. We completely ignored the directions along the RT surface. But in general, there will also be directions along the RT surface. Now, the statement that led to this, that this is always positive, was entirely about the longitudinal directions. So they are actually kind of completely orthogonal parts of the whole set of modular Berry connections. You can exploit it, you can engineer situations where the holonomy is only valid in the longitudinal translational directions, and then you will get this kicks in. Or you can engineer it so that it only is valid in the orthogonal boost directions, and then you're getting some component of the Riemann curvature directly. But these are sort of orthogonal situations. So I think the answer is no.
Okay, thank you.
Okay, and here I have a picture of what the curvature of the Riemann of the Berry connection can look like in real life. Okay, so what we have here is I started from this black RT surface at the bottom. It has a very regular coordinate system about it. There are some uniform ticks here, and there are some arrows which point in the directions of time and space about it. And now I'm going to move it in 2 directions. First, in 2 ways. First to the red RT surface and then to the blue one, or first to and then to the purple one on top. Or I will make it go first to the blue one and then to the purple one on top. And I'm looking at the mismatch between these 2 different coordinate systems that modular parallel transport produced for me along these 2 different trajectories. And you see there is some translational mismatch. Every time 2 arrows are not originating from exactly the same spot, that means I have a translational piece in this Berry connection. And then there will be some boost mismatch, because sometimes like these blue arrows and these red arrows are not aligned completely, but they are related to each other by a boost. And so the boost mismatch is the other 0 mode that I can have produced. So this is a picture of the most general thing you can have locally in a small section of a 1-dimensional RT surface. That's the kind of thing that modular Berry connections give you. Okay. And before I close, I wanted to talk about a third example of the kind of thing you can have, which is the translational example. So remember, we concluded some time ago that whatever modular parallel transport does, it always gives us orthogonal translations fibered over the surface. When the fibering is such that the translations are going in the opposite directions at different points, I'm really doing a rotation. But what if the translations are sort of arranged in the same direction? Then I'm actually shifting the RT surface in a concerted fashion in one direction. So this is the third kind of thing that can happen. And in that case, parallel transport takes me in the orthogonal direction between closest neighbors. So previously we had rotation without slipping. Now we have translation from the nearest neighbor to the nearest neighbor. When I have 2 RT surfaces, there is always one pair of points which are closest to each other. I'm just moving orthogonally from one to the other in that direction. So this is the third type of thing that modular parallel transport can give you. And now maybe I guess I'm over time already, but I want to close with a question which is fun to ponder, which is what are geodesics, but not geodesics in space, but geodesics in kinematic space. So what are geodesics with respect to this notion of parallel transport? I want to remind you that we typically think of geodesics as curves of closest distance. And so far, I haven't given any definition of a metric on kinematic space. So I haven't yet given you any definition of any notion of distance between one region and another region. So maybe we can talk about geodesics. But actually we can, because remember, when we write down the geodesic equation, we only really need the connection term, but not the metric. So it is perfectly possible. It's not a perspective emphasized in GR classes, but it's perfectly possible to solve for geodesics when you have a connection without regard to any, without it being the space being a metric space. Since we already have a connection, we can ask what are the metrics with respect to this connection? Or not the metrics, what are the geodesics with respect to this connection? And so here are two examples of geodesics which are fun. What I have to do is basically ensure that the same operator which is doing parallel transport from RT surface 1 to RT surface 2 will then continue to map RT surface 2 to RT surface 3 and RT surface 3 to RT surface 4 and so on and so on. And that's what we call a geodesic. So this is an example of it. When I have one geodesic and I'm mapping it to another, but then I map it to another and I map it to another, and all of this is being done by the same CFT operator, the same boundary operator, the same translation. This is what we would call a geodesic in the RT surface. And I haven't talked about bit threads at all, but those of you who have studied, well, yes, who have followed developments about the importance of entanglement for the emergence of ADS, of geometry, surely have heard about the bit thread picture of the Ryuta-Kayanagi proposal. What we're really seeing is that a bit thread, which is common to a bunch of RT surfaces, really is a bulk representation of a geodesic in kinematic space with respect to modular parallel transport. We can go back also to example 1, where our modular parallel transport was a rotation without slipping. And in that case, what I have to do is simply continue rotating about the same point, and this also is called a geodesic. And so rotation about a common space-time point also defines a kinematic space geodesic. So this gives you an interesting perspective on what points are from the CFT point of view. It turns out that if I just gave you a bunch of regions in the CFT and I said, this CFT is holographic, find the points in the bulk of the emergent ADS spacetime. One way that we could have done it is simply by asking what are the geodesics in this regime where the regions are chipping away on one side and growing on the other side. In that case, parallel transport is being done by rotation, and geodesics correspond to points in the bulk of ADS. So this is a new and hopefully nice perspective on the emergence of the bulk. Okay, and with that, I'm going to close. Here is some of the picture, some of the stuff that we have talked about of what modular Barry phases can do for us in ADS CFT. I'm sorry I haven't talked about the things outside of ADS CFT that I was hoping to, but maybe in the next edition of the workshop I will. And maybe as I'm closing, I should say thank you very much for the wonderful workshop. And I'm saying this, I imagine, on behalf of all the speakers and all the participants. Thanks so much, and I close here.
Thank you very much, Bartek, for the excellent lectures. So now let's see if there's any question. Like, I mean, maybe you can ask here before we close.
I have one question. Let me try to understand, I mean, your construction. So suppose, so let me consider some meta construction of 1D model. So in the meta, can you translate your, I mean, objective, I mean, in terms of some meta constructed wave function?
When you,
This,
I'm
this
not
may
sure
not
if I
be that well defined. Yeah, I mean, I'm considering some wave 1D wave function, but that can be written in terms of that can be reformulated as some multi-scale entanglement renormalization on such wave function. So applying some disintegral, considering, then I just want, I mean, in order to understand this, your objective. So I
So-
just want to translate some.
uh-huh.
So may
Yeah,
not be
so I don't
that
have
well
a-
defined questions, but
Yeah, so I don't have a picture in terms of tensor networks, but it should be possible to write down a tensor network picture of these, of actually mostly of, where do I have it? Of these two conditions. So first I have a, so what in Mera, the easiest thing to write down is not H mod, but the reduced density matrix. So it would take some exercise with exponentials to recast these equations in the language of where instead of H mod, you're actually featuring reduced density matrices. Well, for the H mod, you would have to take minus the logarithm of the density matrix. So we don't have a nice tensor network representation of that. So it's probably we would have to recast these equations in terms of rows, and you could do that. And then you would find that a V which naturally works is a V that consists of both the, so what we're doing is going from one region to another region. So they have to disagree someplace. Let's talk, maybe it's easiest to talk about the case where I'm just adding an extra region on top of a previous one. So in that case, there is some sliver of the region which we have glued together to the previous region. This V here would be related to the region which lives in the light cone of the right, on the Mera light cone of the larger region, but excluding the light cone of the smaller region. And so there is a piece of Mera that sort of goes along the light cone of the smaller initial region, and that piece would be used to construct V. But that piece would be ambiguous by itself because it's ambiguous by zero modes, and that's where we need condition 2. So in that case, I wouldn't use this for how to eliminate zero modes. Instead, I would, well, let's remember that in Mera, just like in any tensor network, every time I have an interior set of lines meeting, I have a gauge ambiguity of how I can, in what basis I present the internal degrees of freedom, the internal line. I can always, at any two adjacent tensors, I can always glue a U and a U dagger to adjusting to neighboring tensors, and I will have the same state being represented. So there's that ambiguity. And in that case, condition 2 is a statement that I have to present that V, which we found in the first step, in some very specific gauge in Mera, as in I have to use a specific choice of U and U daggers at every line that I have cut to produce V, so that condition 2 is satisfied. This is the kind of thing that you would have to do to read off this generator of parallel transport from Mera. I don't have any more details about this, but I think I just sketched all the necessary ingredients in finding the answer.
I see. Okay, thank you. Let me try to think more.
So I think the important point conceptually is that at Mera, like any other tensor, has this gauge ambiguity. And the gauge ambiguity is about when you draw an interior line, you might as well put a U dagger on that line and then absorb the U and the U dagger into the tensors that are being glued together along that line. And the ambiguity in V that modular parallel transport is trying to fix is exactly that ambiguity.
Any other questions? I actually have one last question. So regarding this geodesic equation that you wrote towards the end, right? Like, I mean, in this kinetic space.
Yeah.
So in principle, we find the geodesic. Don't you need the metric compatible connection? So like the Levi-Civita connection?
Oh, so if you, it's like this. To write the geodesic equation, we just need a connection, no, not the metric. And then to say that geodesic you already found happens to compute smallest distances between trajectories of smallest between pairs of points, you need to then make sure that your metric is compatible with that connection. Okay. We first have a metric and then we find a connection for it. But if you started from a connection and then you were choosing a metric for it, then you would be looking for a connection compatible metric. And I'm saying in any connection compatible metric, that will be true.
I see. Okay. Thanks. Any other questions? If not, let's first thank Bartek again for the very nice lectures.
Thank you very much again.
And then now I think Guignon would like to give some closing remarks for the workshop.
Okay. Hello. So actually, the Sang-Jin was supposed to give a final closing remark, but he had to leave to catch his train. So I'm kind of a substitute for him. Okay, so I will be very short. So because of this corona, our focus program is now changed to online. In some sense, it's a little bit inconvenient because we cannot meet each other, we cannot talk each other. It's a little bit far. But in another sense, there's also good aspect, right? So we can come together more and more, and we can invite many people from everywhere. So and we can discuss online without any big difficulty. So in some sense, it has also good aspect. So probably, I guess next year we also have to do this kind of online conference. But I guess everything will be improved next year. So before finishing, I would like to thank many people. First of all, our technical staff taking care of all this Zoom technology and everything is Hyo-eun Lee in APCTP and Dr. Keun-ho Song. And because of them, we didn't have any difficulty so far. So very nice. And also, I would like to introduce other organizers, Koji Hashimoto, and then Yanis Papadimitriou. So then thank you very much for your nice organization. And finally, I would like to thank all participants of this workshop. And thanks for all your nice collaboration. We made this very wonderful time. Thank you very much. I hope to see you again next year. Okay, thank you.
Thank you also, for the very nice organization. So you took most of the burden, right? I mean, like of organizing this workshop.
But that's a easy thing. So
easy to say it afterwards, I guess.
I'm just writing an email. That's an easy thing. Okay, good. So, yeah, I think we need to talk about next year's program soon.
Good.
So everybody is gone.
So will it be online? Do you prefer online?
So even without Corona?
Yeah.
In my personal opinion, probably we may think about mixed things.
Mixed.
Yeah. So in order to invite these many people, we need to prepare money, right? Much money, but we can save money, but we can talk more in a way. So probably we can think about some mixed one. So partly online, partly offline.
Mm-hmm. So people who can actually come to headquarters of ABCT, then yeah, we have a bunch of people there, but still the talks are online and
Yeah.
lectures. Is that?
Yeah, or we don't need to, invite many people to headquarters.
Mm-hmm.
Small people, but we can have more talks like this. But I think it's also very important to meet each other in person.
Sure.
Yeah, so we cannot, throw it away, even if we have a Zoom technology. That's my personal opinion.
Mm-hmm.
But anyway, next year I think it's definitely Zoom. I don't think the corona will be improved.
Well, yeah, we'll see.
Yeah. Bartek, thank you very much for your very nice talk. And I think I have to say I envy you, because now Beijing is the most safe place in the world.
Just to keep things in perspective, I want to say it's very safe here, but it comes at a cost. So my child is going to school in 2 weeks, and starting last Friday, we're not allowed to go anywhere outside Beijing, because if we go anywhere outside Beijing, he cannot go to school. To go to school, you have to say, for the last 2 weeks, I have been in Beijing. The moment you go out of Beijing, you can't go to school anymore. So, yeah, it's good, it's safe, but it comes at a cost.
But how do you check people really stayed inside the Beijing?
In the case of a 4-year-old like he, it's just his parents' word, because he doesn't have a cell phone. For everybody else, it's by cell phone track.
I see. Yeah, these days GPS technology knows everything. Okay, good. Thank you very much. Bye. See you later.
Thank you. Bye. Bye. Yeah, Bartek, maybe we can. Okay, he left.